So this is our first lecture in the quantum mechanics course. But before we get on to the quantum mechanics, the quantum physics part, we're going to do some kind of underlying physics. These are going to be concepts that are useful for explaining and describing what we're going to talk about throughout quantum mechanics. And these are the concept of fields and the idea of vectors. Those are probably familiar to you if you've done some kind of school or A-level physics and maths. And then the idea of a basis. Now that may be new to most people, but it's going to be really important as we move on to the meat of quantum mechanics a bit later. So what is a field? I'm not going to cover the physics and the philosophy of what one might be. I'm just going to cover the broad types you might encounter. And in this case, we're going to talk about a scalar field. It is essentially a way of assigning a value to every point in space and even time, so that may not even be constant over time. So every point has a value and it may change over time. So have we seen these before? Well, certainly yes, because if you've ever seen, say, a black and white photograph like this one of the Solvay conference, one of the more famous images in science, you've seen a scalar field. So this has a direction to it. There's x and y. So that's a space. It's only a two-dimensional space, but it is still a space. There are coordinates in there. And every point in that space has a number associated with it, specifically from 0 to 255, going from white to black or black to white, whichever way around it goes behind the scenes. And that is a scalar field. But there's an extension to that concept known as a vector field. So a vector field, you're familiar with the word vector, effectively means something with magnitude and a direction. And you'll be thinking of that in terms of the abstract idea of a length and a direction. But you can encode that length and direction as multiple numbers, how far along in an x, y, or z direction you're going, for instance. So a vector field doesn't assign one value, it assigns multiple values. So going with that analogy we started with there, look at a colour photograph. Again, we have an x direction, we have a y direction, so there's a space, again, a 2D space, but it doesn't matter. And every pixel with it has three numbers assigned, specifically the red, the green, and the blue channels, so multiple numbers. And if you're not comfortable with that being a vector space, you can imagine that this number says, how much are we pointing up? The green channel can be how much we're pointing across. The blue channel can be how much are we coming towards us, if I can draw an arrow that sort of comes out of the screen. And if you do look at any colour charts, you can look these up in images, you can often see colours plotted in a three-dimensional space. They can be a vector. So you may have seen these ideas elsewhere. If you look at a weather map, temperature assigns a single value to every point on the Earth's surface. There's latitude, longitude, an x and y dimension, and temperature is its single value. So that would be a scalar field. Wind, on the other hand, well, that has direction and magnitude. Wind must blow in a particular direction. So that is a vector field. So this is specifically a vector field. You can see these arrows pointing in specific directions. There are two other types that we need to be aware of, but we're not going to cover them in too much detail in this course. The first is a tensor field. This is a general version of a vector field and a scalar field. It's a slightly more powerful idea that can add more directions to it. So physicists will be really interested in these because they are really powerful at describing a lot of complicated things. One that we also need to be aware of is a spinor field. These are used to describe electron spins or any kind of particle with a spin. You can imagine it as a vector field, but with, as well as direction and magnitude, a specific rotation attached to it. And those do have some interesting quirks, but we're not going to cover it in too much detail. Just be aware that these two things exist. So we're going to look at a more specific example now, the electromagnetic field. And specifically, we're going to talk about the electric field just for now. Now, the interesting thing about these fields is that we cannot directly detect them. We can't just set up an experiment to say that's the electric field measured. What we can measure, though, is the force that a charged particle experiences. So that force is there on this equation. The little arrow on top tells us we're dealing with a vector quantity. A lot of different textbooks might change that notation a lot. For instance, a common one is to use boldface type for these letters that represent vectors. I'm going to try and stay consistent with the arrow, but if you see something different, know that that also means a vector. So we put a charged particle into an electric field. So the force felt is proportional to that charge multiplied by the strength of the electric field. And because that's a vector quantity, it's also the direction of the field as well as its strength. So the force felt by a charged particle is directly proportional to the strength of an electric field, and that's how we detect it. So how do we visualize that in practice? Well, imagine we have field lines going from positive to negative like so, and we drop a positive charge in there. Well, a positive charge, Q, the charge is equal to -1. We multiply these field lines by +1. We get an arrow pointing the same size and the same direction. And if that particle feels a force, it's going to exhibit some movement. It's going to change its direction, and it's going to follow those field lines. And all that does is, from a slightly more basic principle, reveal what we already should know from school level science, that positive charges are attracted to negative charges. We can swap that for a negative charge. Here Q is -1. So instead of multiplying that arrow by +1, we're going to multiply that arrow by -1. And that is going to actually point in the opposite direction. The same size, same magnitude, completely 180-degree different direction. And that force is also going to induce a movement. And once again, we've developed what we already know. Negative charges are attracted to positive charges. It will begin to move. All from that really simple equation there. Now this one looks a little bit more complicated, but this section of the equation we've already seen. That is the force felt when you drop a charge into an electric field. So we're looking at the force felt by a particle, again, its charge, and then this section, which is the strength of the magnetic field. And here, velocity. So when we usually talk about, say, speed, we just mean how fast something's going. When we say velocity, it is a vector quantity. It has a direction. And because this is a vector, we've got something here which looks like an X, which looks like multiply, but specifically it is the cross product. So if you've done a bit of vectors and it pops up in the math skills course, that will make some sense to you. But how do we end up visualizing that? Well, if we've got velocity heading out in this direction and the field heading in that direction, then the force felt by the particle now begins to move in that direction. So that tells you if you're moving through a magnetic field, you will begin to feel a force that's actually slightly offset to the direction that you're traveling in. And there are some interesting consequences of this, because that is the difference between moving through a magnetic field and staying static in a magnetic field. And I'll drop a couple of videos in the additional information to explain and show what that ramification actually is. Now we've covered some vectors, let's cover the idea of basis vectors. So here we can take this vector that's pointed out in a particular direction and break it down into two constituent parts, namely the amount that is going in the y direction and the amount that's going in the x direction. You may be already comfortable with that. And the end result of that is that if we say that this vector here, E, can be equal to the amount in the x direction plus the amount in the y direction. So we can assemble vectors from those parts as well. So let's assemble it from some parts, because we need to define these directions first. So here we have a vector E pointing in a particular direction, and here we have EY and EX that are defined as basis vectors. These have a direction associated with them, and they also have unit length. Their length is 1. Doesn't matter what that 1 is, it's just a single unit. It is a one step in that direction. But what you can see is the amount that E, our vector, goes in each y direction or the x direction is not a whole unit of these unit or basis vectors. It's actually a multiple. It is a shorter amount. So what we could say is, let's say that E here is equal to, let's call this variable x, a certain number multiplied by the unit vector in the x direction plus another proportion, let's call it y, of the unit vector in the y direction. And so this is the difference here. This length here would be our unit vector. This length here would be our final vector in each direction. And it would be a particular multiple of each unit vector. Now, how do we actually work out what x and y are? Well, if we imagine this is an angle, and we imagine this is h, for hypotenuse, this is opposite and this is adjacent, immediately trigonometry comes to mind. We'll cover that in a bit more detail and specifics later on. Maybe go ahead yourself and try it. You should be able to work out what x and y, those ratios are. So, to recap this first lecture on quantum mechanics, we've covered the idea of a field. So a field assigns a value to every single point in space and time. And vectors encode a direction using multiple numbers. So we have these coefficients, these x or y's, maybe even z's, that define a vector in a particular direction. And then a basis is what we can build vectors from. They can't be broken down into their constituent parts. The basis vectors define these x, y, z directions, or as we get into quantum mechanics, even more complicated spaces.